All right, everybody. So in this video, we are going to go over some questions from Introduction to Chemical Reactions, Ionic Compounds, and Polymers. So let's begin. All right, first question. What is the total number of molecules in the reaction flask before this reaction between hydrogen and nitrogen takes place? Okay. So we are given the final state. Here's our final state. Here's our initial state. They are asking what we should have in the initial state. Okay. And then whatever we have, number and types of atoms in the final state must be same as what we have in the initial state. Okay. So we have 1, 2, 3, 4 nitrogen atoms in the final state. Therefore, when it comes to nitrogen and hydrogen, which are the starting materials, okay, we should have 1, 2, 3, 4, 2 and 2 molecules in our initial state. And when it comes to hydrogen, we have 1, 2, 3, 4 NH3 molecules, giving us 12 hydrogen molecules. So hydrogen atoms, and then we have 4 is 2 molecules, meaning 8 hydrogen atoms. Altogether, we have 20, meaning we have 10 H2 molecules. Therefore, should be 10 for H2 molecules. Altogether, we should have 10 plus 2, 12 molecules in the initial state. The answer is option C. Okay. And then let's move on to question 2. In question 2, we are given the initial and the final state, and you are asked to find the balanced chemical reaction. Okay. So there are a few ways of find the balanced chemical reaction if you are given the submicroscopic representations of the initial and the final states. Let's see. Okay, so we have CH4 reacting with oxygen to produce CH2O plus hydrogen. So that's the balance. That's the chemical reaction. And then straight away we can eliminate option D, because we see that we have reacted in the product side. We do not write reactants on the product side or products on the reactant side in the balanced chemical reaction. Therefore, that is out. And then if you consider something like option B, we can see that we have the atoms are not balanced. Okay, so right away we see 2 oxygen atoms on the reactant side, only 1 on the product side. Therefore, we are missing 1 oxygen atom on the product side. As a result of that, that is out as well. And then if you look at the top one, we have 2 carbons on the reactant side, 2 carbons on the product side. Carbons are balanced. 8 hydrogens on the reactant side. We have 2 times 2, 4 plus 4, 8 hydrogens on the product side as well. The hydrogens are balanced, and 1 oxygen molecule, meaning 2 oxygen atoms on the reactant side, and then 2 oxygen atoms on the product side as well. Therefore, that is balanced. Let's look at option C as well. We have 2 carbons on both sides and 8 hydrogens on the reactant side, and then 2 times 2, 4, only 6 hydrogens on the product side. Therefore, option C is out. The correct answer is option A. Okay, so let's select option A. Moving on, we are given a peg diagram and then asked a bunch of questions. Let's see how to deal with this. What is true about the ionic substance when added to water based on its peg diagram? You can see that the unmixed state has a lower potential in general, one number of configurations, that is going to be always insoluble, because the unmixed state is favored by both potential energy and the number of configurations. Okay, and also we have, because we have a lower potential energy in the unmixed state, the unmixed state should have stronger interactions than the mixed state. So let's see. I think that should do it. The free ions have more configurations than the ions in the crystalline network. Okay, so what we have free ions in the mixed state. Those ions are going to be separated into individual ions in the mixed state, but we have a lower number of configurations there. Therefore, this is not correct. Okay, it seems that the free ions have less configurations, or the mixed state has less configurations than the ionic compound. Okay, ionic compound plus water. All right, and then moving on to option B, ions interact more strongly with themselves than with water molecules. That is correct. So what we have in the unmixed state is ion interactions, or ion interacting, positive ions interacting with negative ions, or ion interaction with themselves. Okay, and in the mixed state we have ion water interactions. So because we have a lower potential energy in the unmixed state, means because we have a lower potential in the unmixed state, we have stronger ion-ion interactions than the ion-water interactions. So therefore, option B is correct. The free ions strongly constrain the movement of water molecules. Okay, so that is really good point. Okay, so we have, even though we have free ions in the mixed state, we have an overall lower number of configurations. That must be due to decrease of number of configurations due to ordering effect. Okay, that means the water molecules are surrounding or ordered around the ions, and that constrains the movement of the water molecules. So that is correct. Ion interact more strongly with water molecules. That is incorrect. Okay, so we know the ion water interactions are weaker because the mixed state has a higher potential energy. Now, the correct answers are options B and C. Okay, let's select them. Moving on. Which of the following compounds is likely soluble in water? And the solubility of any compound is predicted by the charge product, that is charge of the cation times charge of the anion. The absolute value of this, if the absolute value of this is greater than or equal to 4, then it is insoluble. Okay, and if the charge product is less than 4, then it's going to be soluble. Okay. This works most of the time. Right. So if you think about phosphate, or PO3 actually, this is supposed to be phosphate. But anyway, so we know aluminum is +3. Therefore, this must be -3. Therefore, the charge product for the first compound is -9. The absolute value should be 9, which is greater than 4. Therefore, it should be insoluble. Carbonate is -2, potassium is +1, the charge product is 2, therefore this should be soluble. It is insoluble. And then the next compound, strontium, is going to be +2 because it's in the second group, and the sulfate is always -2, the charge product is 4, therefore insoluble. And sulfur is -2, copper is +2, the charge product is 4, therefore it should be insoluble. Then because potassium carbonate is the only one with a charge product less than 4, we can expect potassium carbonate to be soluble in water. Therefore, we're gonna pick that as our answer. All right, here's another question. Okay, the question is, which entity is the limiting reactant in this process? Okay, so the reactants here are H2SO3 and O2. Okay, and the products are H2S and ozone. Okay, and on top of that, you can see that there are some reactant molecules. Okay, these are excess reactant molecules. Okay, these are in excess. Okay, so oxygen or O2 molecules are in excess. Therefore, oxygen cannot limit our reaction. Therefore, the other reactant must be the limiting reactant. Therefore, the limiting reactant is H2SO3. Okay, so let's select that. Moving on. Yeah, let's see. Actually, we can do 2 questions here. Question 6. Arrange the following substances in substances from lowest to highest melting temperatures. Okay, so the melting temperature is going to be related to the ionic force, or the ionic interaction strength between the ions in the ionic compound, and then that is going to be a function of, let's say the ionic force is F, is going to be directly proportional to the charge product, and then inversely proportional to the distance between the ions squared. Okay, so this is what we're looking for. Now to do this, I would determine the charge product first, because charge product is more important than the distance between the ions. So this is going to be the priority. So let's see if we can do this. So we have, let's see, so we have beryllium sulfide, beryllium oxide, and then gallium phosphide and aluminum phosphide. Okay, so if you write the charges out, we have sulfur is -2, beryllium is +2, oxygen is -2, beryllium is +2, phosphide is -3, gallium must be +3, phosphide is -3, and aluminum must be +3. Now for the charge product wise, okay, beryllium sulfide is 4, 4, 9, 9. So we know definitely the gallium phosphide and aluminum phosphide must have higher melting temperatures than beryllium sulfide and beryllium oxide. So it should be like that. Now between beryllium sulfide and beryllium oxide, it's about the distance between the ions. Okay, so in this case, let me draw them. So beryllium is going to be the same size, but sulfur is a larger anion compared to oxygen. Okay, therefore you're going to have a greater distance between the ions in beryllium sulfide than between the ions in beryllium oxide, because ions are the distance between the ions are great in beryllium sulfide, the ionic force must be weaker. Okay, that is depending on this R value, or the distance between the ions. Okay, so therefore beryllium sulfide should have the weakest ionic force. Should have used this. Okay, weakest ionic force, and then beryllium oxide, and then between gallium phosphide and aluminum phosphide, the gallium is a larger ion than aluminum. Let's say this is aluminum. Okay, and therefore the distance between the ions in gallium phosphide is greater than the distance between the ions in aluminum phosphide. Therefore the interactions are going to be relatively weaker in gallium phosphide compared to aluminum phosphide. Okay, because the idea is, if you want to have strong interactions, the ions have to be close to each other. Closer they are to each other, stronger the interactions. Okay, anyway, so beryllium sulfide, beryllium oxide, gallium phosphide, and aluminum phosphide. Okay, so let's see. So we have lowest is 1. Okay, lowest is 1, 2, 3. Highest should be aluminum phosphide. Okay, and then let's do the next one as well. Which of the following polymers shown below is likely to absorb most benzene? Benzene is a non-polar, okay, non-polar compound, okay, with only dispersion forces. Only dispersion forces. Therefore, it is more likely to interact with polymers which are more non-polar. Okay, so it is less likely to interact with polar interactions of polar molecules now, and more likely to interact with non-polar molecules, because like interacts with like. And then out of the polymers we have, all of them have this same backbone. Okay, but this is going to be a polar side chain with hydrogen bonding capability, And you have the same thing here as well. I mean, you have some polar properties of polar functional groups here, but when it comes to this guy over here, I believe this is C. Okay, you have a non-polar side chain. Okay, so therefore it is more likely for the benzene to be absorbed by this polymer rather than other polymers. Okay, so let's go back and enter those answers. Right, so beryllium phosphide is 1, beryllium sulfide is 1, oxide is 2, gallium phosphide 3, aluminum phosphide is the strongest ionic force, highest melting temperature. And then when it comes to question 7, option C is the correct answer, because it's going to be more non-polar, just like benzene. Like interacts with like. Okay, now moving on to question 8. Right, let's take another picture. The question is, select the monomer below that would make the polymer given. So you're given the polymer. Okay, you need to find the you asked to find the monomer that would make this polymer. Okay, so to do this, let's say that I'm going to call this 1, 2, 3, 4, 5. Okay, let's say 6, 7, and 8. Okay, so let's draw it out. Okay, here's 1 and 2. Okay, here's 7, here's 8 with this guy over here, and then to carbon 2 you have 6 attached, and also 3 attached, and then 5 and 4, right? So 4, 5, 3, 6. Okay, so we have 1, 2, 3, 4, 5, 6, and then in the monomer, what's going to happen is, instead of so instead of drawing this 7, this 6 and 7 are not carbons. Actually, those are just bonds coming out to make the connection with the other guys. Okay, so what I mean, I need to clarify that. So these are not 7 and 6 are not actually there. They're just bonds. These are not carbon atoms. Okay, so the idea is between 1 and 2. Okay, instead of that those bonds coming out, you're going to delete those bonds and add a double bond instead. Okay, so those are like hands coming out. These are like hands coming out to connect with the neighboring with the neighbor. Okay, with the neighbor polymer neighbor repeating unit. Okay, and then when it comes to the polymer, those hands are going to go away, and then it's gonna be replaced by a double bond. Okay, and therefore this should be our monomer, which is not B, which is not C, which is not C is absolutely incorrect. Okay, and then you can see that it has to be our it has to be option A. Okay, here's our 1, 2, and then here's 3, 4, 5, and then this we call this 8, and then to 8 we have the other things attached. Anyway, so our correct answer is option A. Okay, now moving on to the last question, question 9. Question 9, you are given you are asked to determine the amount of reactants needed to produce 270 grams of SO2. Okay, whenever we are given a question like this, start with the balanced chemical reaction. We have CS2 reacting with say oxygen to produce CO2 plus SO2. Okay, and then you are to balance this. We see that we have 1 carbon on the reactant side, 1 on the product side. Carbons are balanced. 2 sulfur on the reactant side, 1 sulfur on the product side. So I need to multiply sulfur dioxide by 2. Now I have 2 oxygens on the reactant side, but 6 oxygen atoms on the product side. Therefore, I need to multiply the number of oxygens by 3. Okay. Now what we need to do is we need to we need to start with what is given. Okay, what is given to us is I'm going to do this in a different way than I did in class actually. So what is given to us is the mass of SO2. So we have 270 grams of SO2. That is what is given. Okay, and what I want to do is I want to convert this mass to moles. Okay, to do that, I need to divide this by the molar mass of SO2. So SO2 molar mass is sulfur is 32, oxygen is 16. 16 times 2 is 32. So altogether it should be 64 grams per mole. Should be the molar mass of SO2. And then if I write that, I'm going to have 64 grams of SO2 here, so that I can cancel out grams of sulfur dioxide. And then that's the mass of 1 gram of SO2. I'm sorry, 1 mole of SO2. I meant to say 1 mole. Okay, 1 mole of SO2 has a mass of 64 grams. So I'm going to have that here. So I wrote the 64 grams in the denominator so that I can cancel out the grams in the numerator of 270 grams. Okay, and then what we need to do is we need to have the molar relationship between what we need to they ask you to find the mass of CS2. So before we get to the mass of CS2, we need to have the relationship between CS2 and SO2 in moles. So we can see that in our balanced chemical reaction to get two SO2 molecules, so SO2 moles, I need to have only 1 CS2 moles. Okay, so therefore that is the relationship. Now again, the idea is to cancel things out when we set this up. So I'm going to have the moles of SO2 in the denominator. Okay, so let me have the moles of SO2 in the denominator. So what we have is 2 moles of SO2, and then to get 2 moles of SO2 according to the balanced chemical reaction, this is my 2. Okay, I need 1 mole of CS2. Okay, now the beauty is I can cancel out more SO2 in a second. Okay, and then the question is asking for the mass. All right, now I need to have the mass. So in the numerator for sure. So let's use the molar mass of CS2 to get the mass. So the idea is 1 mole of CS2 is going to weigh, let's say carbon is 12, sulfur is 32. You have 2 of them, that's 64. 64 plus 12 is 76. It's 76 grams. 76 grams of CS2. In 1 mole of CS2, you have 76 grams of CS2. Okay, now what we want to do is we need to start canceling things out. Okay, so grams of sulfur cancels out, moles of SO2 cancels out, and moles of CS2 cancels out, and then you're going to get the answer in grams of CS2, which is what the question is asking. Okay, now let's plug and chug these values. We have 270 multiplied by 76 in the numerator, and in the denominator we have 64 times 2. Okay, and then if you do this calculation, you can plug and chug in your calculators and let's see what I'm going to get here. So 270 times 76 divided by 64 times 2 is 160.3. I get 160.3 as my answer. All right, I'm going to try that out. Let's see. Okay, 160.3. 160.3. Okay, now that's it. I think we completed all the questions. I'm going to submit the quiz and see what happened. Okay, so I just submitted the quiz. There you go. You got all the questions correct. All right, everybody. So I hope this video helped. The idea is to show you the way I think about the problem when I apply the knowledge to solve the problems. Yeah, I'll see you guys in class. Bye, everybody.